Hey, cool kids and Red Devil chemists, it's Coach Scott. Let's go on with our study of quantum mechanics and let's talk about electron configurations. Let's start talking about orbital diagrams. So, orbital diagrams are a shorthand way to illustrate the energy levels of electrons. All right? Each one of those boxes uh, represent one orbital. Orbitals in the same subshell are drawn together. The arrows represent the electrons. Now, the directions of the arrow represents the spin of that electron, either positive or negative, or right or left hand spin, however you want to look at it. So this is an example of oxygen, which is atomic number 8. That means it's got 8 electrons. So you can see if you count them 1, 2, 3, 4, 5, 6, 7, 8 electrons. That would be the orbital diagram. So you can also put these vertically, and that illustrates the increasing energy of the orbitals. So in order to do either one of these orbital diagrams, you've got to know how many electrons the atom has. So in a neutral atom, the number of electrons equal the number of protons. We covered that after about the first or second week of school. So the number of electrons will be the same as the atomic number. So let's do a quick check. In an electron orbital diagram, the individual box represents what? Pause. And of course, you guys said the orbital. That's what it represents. In an electron orbital diagram, which symbol represents an electron? Well, that represents an electron, and that represents an electron. So this one would be both B and C. Okay. In an electron orbital diagram, the three orbitals together, that 3p, indicates each orbital occupies what? Pause. The same energy level, right? That would be the same energy level. So, when we do orbital diagrams, all right, we've got three principles or three rules, if you would, in order that we have to use in order to, see if I got it drawing yet. No. That we're going to have to use whenever we fill them. It's just that's the way it is. I don't know what's going on there. Okay. So the first one is the off-bow principle. And what it's saying is that the electrons are added one at a time to the lowest energy orbital available until all the electrons of the atoms have been accounted for in that level. There's also the Pauli exclusion principle, and it states that an orbital can hold a maximum of 2 electrons. All right. To occupy the same orbital, the 2 electrons must have a opposite direction spin. Then there's Hunds Rule. If 2 or more orbitals of equal energy are available, electrons will occupy them singly before filling orbitals in pairs. So, the Aufbau principle. Aufbau takes its name from a German word that means building up. All right, building. So, this principle was developed in the 1920s by Bohr. Of course, his model went away, so he started working with other stuff on quantum. Bohr and Pauli. And it states that the electrons will fill the lowest energy orbitals first. So if you think about this like a hotel with no elevator, you don't want to walk up to the top floor if you can get a room on the first floor. So you're going to fill that first floor room first before you fill the 4th floor because you have to walk up the stairs. And that's what that's really sort of saying. Okay. Now our second rule we're going to have to worry about is what we call the Pauli exclusion principle. It states that no two electrons in the same atom can have the exact same quantum numbers. It can't have the same address, right? So we've got to do these on our diagrams to where they make sense. The quantum state is specified by the 4 quantum numbers. No two electrons can have the same set of quantum numbers. So it's either got to be a positive spin or a negative spin. So when I add these up, these arrows, if they're 2 in one subshell, they have to be either up or down, never like this. Never going in the same direction. It can't happen like that. Okay. Now Hunds Rule. It states that every orbital in a subshell is singly occupied with one electron before any one orbital is doubly occupied. All right? And all of the electrons in the singly occupied orbitals have the same spin. So those need to be, if they're going up, they all need to be going up. So in other words, all right, you can think about a bus. All right? If you're the first person on the bus stop, at the first bus stop, you're going to get whatever seat you want, but you're going to get up close to the driver because you don't want to walk back. You're lazy, like me. All right. Now, if you're the second person, you've got all those empty seats. Are you going to sit right next to that person? It's probably somebody you don't really like that much. No, you're going to go to the next empty seat because you don't want to share a seat, right? It's almost like being on an airplane. You don't ever want to get the middle seat because then you don't have any butt room, right? So you always want either the aisle seat or the window seat with nobody in the middle, right? So you're never going to try to get somebody by yourself. The same thing with electrons, all right? If there's an empty seat at the same energy level, it's going to go into that particular spot. All right. So let's say we're going to fill, and I'll do a sample of this. We're going to fill the energy level diagram for magnesium. So I've got my trusty periodic table, and I see that magnesium has an atomic number of 12. And we'll work in class if we need to remember how to find out what the atomic number is. So magnesium has an atomic number of 12. That means there's 12 protons and 12 electrons. So I'm going to start filling these up. So I'm going to put one arrow in. All right. Now, by off-bow principle, I've got to go from the bottom to the top. I've got to have opposite spins according to the Pauli exclusion principle. So that's one up, one down. I've got 2 electrons. Off-bow principle, I've got to go up to the 2s level, and that's where I go. And again, 2 electrons. So I've got 2 there, 2 there. So I've got 4. I need to get 12. Now, I'm going to start filling the 2p level. According to off-bow principle, that's the next higher energy state. So I'm going to put 1 electron there. I'm going to get in the habit of not putting my electron going down here. All right. So I'm going to go by Hunds Rule. I'm going to fill these up before I start putting my down arrows. So there's 1, 2, 3. All right, so everybody's got their own room now. Now we've got to go start setting in the seats again. So I got to sit next to somebody. There's only 3 seats. Let's see what my total is. I got 4, 7. So I got 4 plus 3, that's 7. So I've got 9. I've got 8. I've got 9. Now I've got 10 electrons. Everything's cool. I'm going by off-bow principle. I'm following Pauli exclusion, and I'm following a Hunds rule. So I've got 2 more electrons. Let's see, I'm going to put one there. Can I put it in 3p? No. I have to go into the 3s, and the 2 electrons are there. So that's the orbital diagram, the energy level diagram for magnesium. Now it's asking me to do chlorine, so let's do chlorine again. And I'm going to let you take a break, and you're going to try it by yourself, then I'll come back and do it. Got my periodic table. Chlorine has 17, atomic number 17. I'm going to write it right there so I don't forget it. So I'll give you a moment, pause your video, you try to draw this diagram, and then I'll do it. Okay, unpause. So I've got 17 electrons to fill. There's 2. I'm following all my rules. There's 4. There's 5, 6, 7, 8, 9, 10. Still got 7 more to go. There's 12. All right. 13, 14, 15. Got 2 more to go. Now notice I followed Hunds Rule. I put each of those in their own orbital before I started filling up. Now I'm going to go Pauli's exclusion principle. All right, there's 16 and there's 17. I've got 1 space left in that subshell. There's the orbital diagram for chlorine. Now we're going to do iron, Fe. Iron, looking at my periodic table, has 26, atomic number of 26. If you want to try and do this yourself, I'll come back and I'll get it done. We're back. So 1, 2, 3, 4. 4. And let me fix this. Okay, guys, I had to kill that and come back. So we're doing iron 26. So I'll start drawing my electrons. 1, 2, 3, 4. And I'm getting the habit of doing all the rules. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, whoa, 16, 17, 18, and this is doing that again. 18, 19. I'll be right back. Okay, so I restarted, so I'm back where we were. So if you count it, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Again, we got to put 26 electrons in. So I'm going to go down to 4s. That's 19 and 20. Now look, the 3d orbital subshell has lower energy than the 4p. So now I've got to go down to the 3d and fill it. All right, so I'm at 20, 21, and I got to fill this one next. 22, 23, 24, 25, and finally 26. So that would be iron's energy level diagram. So the orbital diagram depicts electrons in which element. So now all we got to do is count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look at my periodic table. 13, of course, is aluminum. Not hard. The orbital diagram depicts electrons in which element. I'll let you do this. I'll pause. And of course, you count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is, of course, neon. Element number 10, atomic number 10. Now, which rule or principle is violated in this diagram? And those are the three rules. Off-bow says you fill the lower energy orbitals first. Well, they're all filled and they're the lower energy orbitals. Poly, electrons in the same orbital cannot have the same spin. Well, those have different spins. Ooh, this does not. So this is violating the Pauli exclusion principle. Which rule or principle is violated in this diagram? Well, let's see. We're going off-bow good. It's going from the bottom up. 1, 2. Both of those have opposite spins. Oh, but look, right there. We're violating Hunds Rule. Orbitals are all occupied before any are double occupied. So this violates what? Hunds Rule. Move on. Which principle or rule is violated in this diagram? Said off-bow, you fill lower energy orbitals first. Boom, got that. Poly, electrons in the same orbital cannot have the same spin. Well, nobody has the same spin in their different orbitals. Orbital Hunds Rule. Orbitals are all occupied before any are doubly occupied. Well, we're good to go on that, so that's got to be C. None of them. That is a good orbital diagram of element number 7, atomic number 7, nitrogen. Which rule or principle is violated in this diagram? Well, let's see. Let's look at off-bow. Fill lower energy orbitals first. Ooh, right there. There is no, oh, yeah, they filled those, so that is violating the off-bow principle. Which rule or principle is violated in this diagram? Oh, there's several. One, we're violating the off-bow principle. All right. Oh, and look, we're violating the Pauli exclusion principle because those have the same spin. I don't see where we're violating Hunds Rule because, well, they're not there. So that's violating enough. So, guys, that's where we're at. We're at the orbital diagrams. We've got those. So we'll practice those in class in our collaboration time. So other than that, Coach Scott saying, have a wonderful Red Devil day and deuces.